Hello, Chem 201 Organickers. We have another topic that we need to cover in order to prepare for learning organic chemistry, and this one would be about intermolecular forces. So hopefully every prerequisite class has discussed at least a little bit the topic of intermolecular forces. We're going to use intermolecular forces in organic chemistry to predict and evaluate potential physical properties such as melting point and boiling point, solubility, that sort of thing. So we do need to review a little bit about what an intermolecular force is and how am I going to be able to decide when I look at a molecule what type of intermolecular force is going to be the dominant force in that molecule and thus control physical properties. So let me start sharing my iPad. Okay, so we want to look at a review of intermolecular forces. So remember that an intermolecular force are those attractions between molecules that hold them together. These forces are electrical in origin, and they result from the mutual attraction of unlike charges or the mutual repulsion of like charges. Intermolecular forces between molecules is different than an actual chemical bond. Covalent bonds and ionic bonds are actually considered to be intramolecular forces, and they are much, much stronger in general than any of the intermolecular forces that we're going to talk about. So we are going to talk about several types of intermolecular forces. We have ion dipole forces, and as described, those would be interactions between ions and then molecules that had dipole forces. We have a grouping called van der Waals forces, which include dipole-dipole forces, London dispersion forces, and also hydrogen bonds. So these are the types of intermolecular forces that we need to know a little bit about and that we're going to use in order to assess organic chemical structures and figure out what kind of physical properties that we might be able to expect in any particular type of molecule. So let's start with ion dipole forces. These forces are the result of electrical interactions between an ion and the partial charges on a polar molecule. So here you have an anion, which is a negatively charged anion, and here you have a cation, which is a positively charged ion. Now notice if I have a compound that has a permanent dipole, right? A polar molecule. We talked about that when we looked at molecular polarity. I'm going to have regions that are partial positive and partial negative based on the permanent dipole that is present in this molecule. So, because opposites attract, these polar molecules are going to orient themselves so that they're going to attract the partial positive part of the molecule is going to be attracted to the negative anion. So the molecules themselves are going to orient to maximize that oppositely charged attraction. The partial positive parts of many molecules are going to orient themselves to interact with that negatively charged anion. In the same solution, you're also going to have the opposite occurring. So here I have a positively charged cation, and then my polar molecule is going to orient so the partially negative part of the molecule is going to interact with that positively charged ion. So these forces, these interactions, between the polar molecules that have permanent dipoles and the positive or negatively charged ions are what you would consider the ion dipole forces. And these are pretty strong. In general, the more polar something is, the more I have a positive or a negative charge, the greater the force is. So this is probably the strongest intermolecular force that we're going to be talking about today. Now, those groupings of van der Waals forces, one of them is called dipole-dipole. Again, if a molecule has a dipole, it's a polar molecule. Well, so dipole-dipole forces are where I have electrical interactions that occur among dipoles on neighboring molecules. Remember, intermolecular force, which is going to be between molecules. So my polar molecules are going to attract one another when they orient with unlike charges close together, right? So here I have this negative with the positive with the negative with the positive with the negative, and so on and so forth. So here I'm maximizing those opposite charges. I am attracting, these molecules have an attractive force between each other, which is electrostatic in nature, because the partial positive parts of the polar molecule are going to orient so that they're close by to the partial negative parts of those of themselves, another polar molecule. Here, they're going to repel each other, right? So these positive interactions is a repulsion. And what happens is you're going to have a sort of spontaneous and natural alignment where these positive and negative charges sort of align so that they can interact. And this force is actually, again, pretty strong because I have permanent dipoles in these molecules. So I always have a partial plus and a partial negative part of the molecule. So again, this is the mid-range force in the van der Waals. It's stronger than London dispersion, which we're going to talk about, but it is weaker than hydrogen bonding. So again, dipole-dipole forces. Here, you can look at 3 different compounds. This is nonpolar. I only have carbon-carbon bonds and carbon-hydrogen bonds, which are all nonpolar. Here, I have a little bit of polarity because when I have this CH3O, I do have a polar bond, right? This is going to be a polar bond. It's going to be bent molecular structure. And I'm going to have my net dipole, which is kind of go up the middle. And then here, this is also polar because I have my methyl group, my CH3, and then I have my CN, which is that sort of cyanotype group. And this also has a dipole that goes in this way. So this is a polar molecule as well. Now, this number indicates the amount of polarity, right? So the lower the number, the lower the polarity. So if I increase dipole moment, I increase polarity, right? So this guy is going to be the most polar. Now, this is also important. I have to be able to compare apples to apples. If I have really large discrepancies in the sizes of the molecules, I don't know exactly what's going to happen in that case. So what I want to do is make sure that, what did I do? Is to make sure that I'm comparing the same type of structure. So these guys are actually, oh well, I'm just gonna leave it. So these guys are actually the same molecular weight, more or less, which means they're sort of the same size. Now, if you notice here, as the dipole moment increases, the intermolecular forces increase. The more polar than I am, right, the stronger the dipole and the stronger the dipole-dipole interaction. As intermolecular forces increase, the boiling point increases. Notice that this is the largest boiling point and this is the smallest. And this is sort of increasing as I increase polarity, right? So this is because if I have a very strong intermolecular attraction, what I'm going to have is, it's going to be harder. It's going to require more energy in order for those molecules to be pulled apart. Remember, solids are really close together, very packed together. Liquids are sort of in between. They're packed together, but they can flow. And then gases are really far away from each other and they're moving fast, high kinetic energy, right? Well, to phase change, when I go from a solid to a liquid and a liquid to a gas, I have to pull those molecules apart, right? From solid to liquid, which is melting, I have to pull the molecule apart. The stronger those molecules are stuck together with these intermolecular forces, the harder it is for me to actually pull them apart, which means my boiling point is going to increase. Now here, I'm going to talk about London dispersion forces. Typically, my electrons are moving around all over the place in those electron clouds around in the atom, right? So most of the time, let's say it kind of evens out and it's symmetrical. This would be in a non-polar situation. My electrons are sort of evenly distributed. I don't really have a partial negative or a partial positive anywhere. This is all sort of symmetrically distributed. Now, at any given instant, the electron distribution in a molecule may be unsymmetrical. So at a particular instant, I get an instantaneous dipole, which means at that moment, more electron density is on this side and less electron density is on this side, right? Now that just happens randomly, but what it creates is a temporary dipole, an instantaneous temporary dipole. But now this molecule sees this molecule. This partial positive is going to attract the electrons to it, which means now my next molecule is going to have an induced dipole. And now I'm going to have this positive negative interaction between, which is my London dispersion force. So I have an instantaneous random temporary dipole that just happens to occur. When it does occur, it's going to induce a complementary attractive dipole in neighboring molecules. And it's this interaction that is called our London dispersion forces. This is the only intermolecular force in nonpolar molecules. So this is the only intermolecular force in nonpolar molecules. This force is in every molecule. So this force exists in all molecules because this random dipole happens a lot because my electrons are moving around. The issue is my dipole-dipole interaction is much stronger than this. My hydrogen bonding interaction is much stronger than this. So those forces are a lot stronger than my temporary London dispersion forces. So the stronger force tends to dictate what physical properties occur in the molecule. So in nonpolar molecules, the physical properties are resulting from the strength of these London dispersion forces, which are temporary, instantaneous, and induced dipoles. There's a couple of factors that we have to look at when we want to assess the magnitude of London dispersion forces. Here, I have my lowest molecular weight. Here, I have my highest molecular weight. This is larger and more polarizable, right? Here, my fluorine, you know, my electrons are really close to it, right? That's my fluorine. Now I have iodine, which is much larger. So these larger clouds can fluctuate, can move around more, which is called polarizability. So I can create these larger dispersion forces because I have more electrons in a larger surface area. So as you notice, as my size increases, my melting point increases, right? So as London dispersion force increase, the magnitude of that force increases. As the magnitude of that force increases, the boiling point and melting point increases because now it's harder to pull those molecules apart and create a phase change from either solid to liquid or liquid to gas. London dispersion forces are also not just molecular weight, but they're also dictated by surface area. So this is a long, skinny molecule. And it has a lot of surface area, right? It has a lot of surface area. So when another molecule that looks like it is next to it, I have this huge interface for interaction. This is going to be sort of shorter and not so, this is going to have lower surface area because the molecule is more compact. So now if I stack another one, I'm only going to have a very small interaction here. So if I increase surface area, I increase my London dispersion forces, and I'm going to increase the melting point and boiling points because now those intermolecular forces are a little bit longer or are a little bit stronger, and that's going to influence the energy it takes to pull them apart. So notice in this pentane, which is long and skinny and has more surface area, the London dispersion forces are larger. I have a larger boiling point than in this molecule, this 2,2-dimethyl propane, which is branched and much more compact. So that experiences weaker London dispersion forces, and it has a lower boiling point as a result. Now, another really important intermolecular force is hydrogen bonding. This is a special case of our dipole-dipole interactions. And it's the strongest of the van der Waals forces. So it's stronger than dipole-dipole interactions. It's stronger than London dispersion forces. It's an attractive force between a hydrogen atom. I must have a hydrogen atom, and this has to be bonded to a very electronegative atom, which is oxygen, nitrogen, or fluorine. I have to have an HO, an HN, or an HF. Now this is hydrogen fluoride, that's a molecule. So in organic chemistry, I'm really gonna notice that my alcohols, which are OH, and my amines, which have NH, those are gonna have my hydrogen bonding capabilities. So what is this bond look like? I have a lone pair, and then I have this hydrogen-oxygen bond, or I have a lone pair, and I have a hydrogen-nitrogen bond. My lone pair is very partial negative, right? Water is very polar. The lone pair is now interacting. Now, why is this H plus is basically called, is basically a bare proton, because hydrogen only has one electron. So when hydrogen loses its electron density, it actually becomes pretty much a bare proton. So oxygen, fluorine, and nitrogen are electronegative enough where all this electron density is really pulled away from the hydrogens, which means that these are pretty extra specially positive. And because oxygen is more electronegative than nitrogen, and OH forms a stronger hydrogen bond. There are other reasons for that that we'll discuss later in the class. But what you're gonna see now is that I have this hydrogen bonding interaction between these molecules. If you notice, H2O has a boiling point of 100 degrees Celsius, but it's only 18 grams per mole in terms of its atomic mass, or in terms of its molar mass. It's 18 AMU in terms of its atomic mass. Now, boiling points of 100 degrees, that's basically a measure of the strength of that hydrogen bond. It takes a lot of energy to pull water molecules apart from each other and go from liquid to vapor phase. So it's so much higher than you would expect for something that has that small amount of a mass. And the reason that boiling point is so high, comparatively speaking, is solely due to the magnitude of this very strong intermolecular force, which is considered to be this hydrogen bond. Here is what I'm talking about in terms of water. Liquid water actually contains a vast three-dimensional network of hydrogen bonds, which result from the attraction between those positively polarized hydrogens and the electron pairs on negatively polarized oxygens. Each oxygen, right, the red molecules are the oxygen, each one of those oxygens can form two hydrogen bonds. So the hydrogen bonds are these dotted lines, because oxygen has two lone pair, right? If oxygen has those two lone pair, another hydrogen from an oxygen molecule can form that attraction. Another one from another hydrogen or a water molecule can form that attraction. So this is the reason I form a hugely vast connection of hydrogen bonds in water, which is why, relatively speaking, the boiling point of water is so high. One interesting segment, if you're going into biochemistry, if you've talked about biochemistry in a biology class, the alpha helix double-stranded DNA is actually held together by hydrogen bonds between the two different chains. So those nitrogenous bases that are present in DNA and RNA, when DNA coils and forms the alpha helix, it's those hydrogen bonds between those chains that actually control that molecule and keep it together. Now, this is interesting. Hydrogen bonds are relatively strong, but in order for DNA to replicate, I also have to break them apart so I can induce replication in my DNA strands, right? So those strands have to uncouple, they have to break apart. Breaking the hydrogen bonds requires energy, but the hydrogen bond isn't nearly as strong as an actual chemical bond, like a covalent bond. So this is perfectly suited for what the DNA has to do. It's the hydrogen bonding between these nitrogenous bases is strong enough to keep everything together, but it's weak enough so that that can unzip and allow replication to occur. Just to summarize, we talked about 4 different intermolecular forces. I have ion dipole, right? I have dipole-dipole, I have London dispersion, and I have hydrogen bonding. So remember, ion dipole is between ions and polar molecules. If I look at dipole, I have to have a polar molecule, so I have to have a permanent dipole in order for this force to be present. London dispersion, remember, all molecules, and the strength is going to depend on the size and the polarizability. And then in terms of hydrogen bonds, I must have a hydrogen attached to an oxygen, a nitrogen, or a fluorine. I have to have that higher difference in electronegativity, and I have to have hydrogen, which then becomes basically a bare proton in order to maximize that type of electrostatic interaction. That's all that I have, and hopefully this will give you a little update on what you need to know. I will be talking about intermolecular forces throughout when we look at physical properties of the various functional groups that we're going to talk about. So when we do this all together, we'll be able to hopefully be on the same page. And if you have any questions, don't hesitate to reach out and let me know how I can help you. All right. So that's it for today in terms of intermolecular forces. I will be back later.